Thank you, Vasu. Yeah, and thank you for inviting me. Uh, it's kind of a pleasure to talk about this work because it's so new. It's kind of still in process. So yeah, so everything shown in this presentation is almost unpublished. So it's, yeah. Okay, so I'll be talking about subtleties of using of Bayesian inference for parameter estimation. So, I mean, parameter estimation, the term itself says that, okay, we are trying to estimate parameters from something, and Bayesian inference is the technique I use it. And then I'll be talking about, like, okay, lots of people talk about Bayesian inference for parameter estimation. And while working on this project for last 1 year almost now, um, I gained certain insights which weren't very apparent, and I'll be sharing those with you today. So, so the main motivation of using Bayesian inference, or the whole motivation behind this project, is very simple. And just to mention that today I have tried to keep the talk as general as possible because I mean the organizers said that there would be people from various different fields. So I will try not to talk about just PV. So it's more general, yeah. So the motivation is that like in any kind of devices that we deal with, like be it battery, be it PV, some other electronic devices, or whatever, the performance of those devices are kind of determined by the materials we are building it with. Like say in a solar cell, it's the absorber layer and the contact layers, whereas in a battery, it's the electrode materials, the electrolyte, and everything. And most of the time we actually do not know what are the material parameters, like the mobility or maybe the diffusivity constant. We don't know these material parameters, but it is this material parameters that would effectively determine how well your device is performing. And then if we do not know this material parameters of the materials that we are using, then we do not know what might be limiting our performances. Like the mobility of one of the layer could be very low, or the diffusivity constant of the electrolyte could be very low. Something might be going wrong, and we have no way to figuring that out. So this method kind of helps us to deal with these challenges. The challenge, well, people has been doing parameter estimation for quite some time. What we do, we have some experimental data, and we try to fit our model to it. And what we do, usually we try randomly, like a bunch of parameters, try vary this and see, okay, does it fit? Does it fit? Okay, it doesn't fit, and we throw away the data, right? And the problem is oftentimes, even varying the parameters quite a lot has very like subtle changes to our output characteristics. For example, in here, I just plotted 4 random JV curves using my device simulator, and I actually varied the 4 parameters that are given inside the box. And if you look carefully, I vary, say, the SETL, which is the surface recombination velocity at one of the transport layers of our photovoltaic device. And I vary it from, say, 1 centimeter per second to 100. So it's like 2 orders of magnitude. And you see that there is very little that's actually changing in these 4 JV curves. And then when you are doing parameter estimation using using the normal methods that we use, how do you know which one is our correct parameter set? We don't know that. And this is one of the challenges that we oftentimes face while explaining or trying to explain what our experimental data is trying to tell us. And one of the solutions that can solve these challenges is Bayesian inference. So what if we had a method which actually takes, for example, you have some experimental data, it takes those experimental data as inputs, and then you also give it some simulated data, and comparing the experimental data with the simulated data, it can actually give you the probabilities or say the ranges in which the material parameter could exist. And like that is already quite good, but even beyond that, it can also tell you how some of the material parameters can be correlated. For example, if you increase the mobility, your lifetime can also increase. So like the mobility lifetime product is a very good example in PV, which has to be constant. If it stays constant, then you do not see a huge variation in your output. So this kind of intercorrelations between the parameters can also be found from this Bayesian inference technique. Now, there are certain applications to Bayesian inference, and one of them is definitely what I'm talking about today is parameter estimation. So oftentimes in device physics, or I don't know, maybe in other fields also, you have a numerical simulator solver, which you always try to fit your experimental data with. And there are tens of parameters in there, and you need to fit those. And this method is good for that kind of problems of parameter extraction. Also, you can there was a paper from Tonio's group. I think it was in NPJ computational materials, where they actually showed a way to relate the experimental temperature of fabricating some kind of a solar cell to the material parameters. So Bayesian inference can also be used for linking the experimental observables to the material parameters. Another thing that it is good for is for root cause analysis, which is actually a derivation of the parameter extraction, to be honest, because if you know the parameters, if you find the parameters that your device has, then you automatically see very clearly that which is the portion of your device that kind of limiting your device. And then from there, you can use better materials or other processing techniques to improve to eliminate such root causes. So at the core of Bayesian inference is this Bayes theorem. And what does Bayes theorem tell us? Or what does it do? So in Bayes theorem, we are trying to estimate the posterior probability density, which is like, the distribution of your material parameters, or the range of, or in which range does your material parameter actually lie? Like, you can have your mobility, you can vary it for, say, 5 orders of magnitude, but where does the mobility actually lie in that 5 orders of magnitude range? Then comes this is the posterior probability from the left-hand side of the equation. On the right-hand side, what we have is the prior probability, which is like, what is your belief? So suppose your mobility again, you vary the range of mobility for 10 to the power for 5 orders of magnitude, and you have no clue where it is. So you can quantify the belief saying like, okay, I have uniform belief in all my material parameters, or in all that range, that it can lie everywhere. So the prior can be uniform, or what we call as uniform prior, when you have equal belief on all your material parameters. You do not have a bias for anything. And the final part is the likelihood function. The likelihood is basically the error between your model data that you get from the guessed material parameters. So for example, you are trying to fit a JV curve, and you said that, okay, probably this combination of material parameters is my material parameter that I think it is. And then you use your simulator or your equation, whatever, to generate a JV curve or something. And then you compare those two. And then you calculate the error. And that error in some form is the likelihood function. I will not go into the mathematical details. I've avoided all equations. I'm just giving you a general idea, so that the error between the actual experimental curve and the simulated JV curve obtained from your guessed parameters is the likelihood function. And the higher the error is, lower is the likelihood function. That basically means that that set of material parameters have a very little likelihood of actually generating your experimental data. So it's not likely that that particular set of material parameters is your true ground truth. So now, okay. So using this concept of Bayes theorem, or based on this concept of Bayes theorem, we actually developed a workflow for performing Bayesian inference. And there are 2 distinct parts to this workflow. The first part is basically working with a lot of data. So first, you need to generate a huge data set. And so that's the data generation part. Then there is a data processing, and then the surrogate model training. Now, this part is not exactly Bayesian inference. So we are not doing Bayesian inference in this part, but this is like, without this, we cannot do the Bayesian inference. And the last part is Bayesian inference using Markov chain Monte Carlo, another sampling technique that I will come to in the next slide. But before I go on there, I would like to actually highlight, why do we need this surrogate model? So what is a surrogate model, first of all? The surrogate model is like, it works like an alias of your actual device simulator. Now, actual device simulators are oftentimes slow. For example, the device simulator I was using, it can run like twice in 1 second. And that means on a 2-core laptop, if I can make it run, it will run. If I can, first of all, if I can make it run in parallel, which I couldn't, if I would have, then it would have run say 4 times in 1 second, right? And that means if I was going to do or use it, then I would need a lot of time, because every second it will just run 4 times. Whereas a trained surrogate model, it is like multiple orders of magnitude faster. So we first generate a huge data set that we train the neural network on to develop the surrogate model, and then we replace our device simulator with this surrogate model. Then the surrogate model, as I said, is orders of magnitude faster than the device simulator. And honestly, it's like 1,000 times faster, or more than 10,000 times faster. So there is no comparison between the two. And finally, why do we need this speed enhancement? We need the speed enhancement because otherwise we cannot do Bayesian inference using Markov chain Monte Carlo. Like the other course that I have seen uses grid factorization or everything or something else, which actually uses the device simulator. And I feel that those processes probably would be slower. So now going back to Markov chain Monte Carlo. So yeah, well, this is I realize that this figure kind of looks like a watermelon to me somehow from the title slide. Yeah, I don't know. Yeah. So what is Markov chain Monte Carlo? Markov chain Monte Carlo is a sampling technique, first of all. So people, I mean, most of us probably know what a sampling technique is. It's like you have a parameter space or kind of a hyperspace where you sample different points and see what each of those points give you as output. Now, there is a random sampling technique in which you would have you will sample points randomly in your hyperparameter space. But when you are dealing with a large number of parameters to extract, then random sampling technique will not work because the problem becomes intractable. If you I was using it in my problem, I have an 8-dimensional hyperparameter space, so it wasn't possible. So we use this thing called Markov chain Monte Carlo, in which what it does, we have a number of walkers. Here, I mean, some walkers are running, yeah. And what these walkers do is that the walkers are samplers. So at every iteration when Bayesian inference runs, these walkers will sample some points in the hyperparameter space. And at each of those points, using the surrogate model, then I would actually predict the output for all those thetas. By theta, I mean the combination of material parameters that each walker is sampling. So using the surrogate model, I will generate the output for those theta values. Then I will calculate the likelihood function within the algorithm for Bayesian inference. And then once I have done that, then the thetas, so there will be multiple thetas in every iteration. So I use something like 256 to 512 walkers for my calculations. That means at every iteration of Bayesian inference, there are 512 unique outputs that are being generated. Now, some of those theta values will not be good theta values, like say their likelihood would be very low, and then those are rejected. And the ones their likelihoods are higher, they're accepted. For example, in this figure, actually, I show it. So suppose the walkers start over here at this point on the red point on the extreme left, and then they sample another point there, and that point is also accepted. But now the third point they select is this dashed circle. It has a fairly low likelihood. So this point is not accepted, and it returns back to the original or the second point and samples another. And that's how it progresses through time or through iterations. And those accepted theta values actually form my Markov chain. So the Markov chain in Markov chain Monte Carlo is basically a array or say a matrix of theta values from different iterations which have high likelihood. Once we have the Markov chain, and then we can plot a histogram, and from that histogram, like over here I show. So for example, in this first range, there was only one point that was accepted. So say I represent it like this, just with one theta. In the second case, there were 3 theta values that were accepted, so a little bit higher probability. In this midpoint, we had 5, so it has the highest number of accepted theta values in the Markov chain, and so on. And then I can, so this is like a histogram, and then you can approximate the posterior probability of your parameters from this histogram. So this is technically what Bayesian inference is, that you sample sort of randomly, or this is the core idea of Bayes' theorem, that if you can sample your space randomly or in a certain way, then you would get an estimate of what the distribution would actually look like. So we sample the entire parameter space, and then we try to estimate from that distribution, from that sample space, that what our distribution of parameters actually is. Now, okay, I talked about very abstract things. I want to show you some results here. And so our end goal is to estimate parameters. And I use the one diode model, which is fairly simple, to explain how it works. So at first, on the first graph on the left, I show the actual current voltage curves used, or current voltage curves that I got using a one diode model by varying 4 different temperatures. So it is 300, 400, 500, and 600. And like the temperature variation. And so, and I kind of concatenated. So the JV curves are placed one after the other. So when you plot it along an arbitrary x-axis, it kind of looks like this waves. And then, so there is a data generation part. Then you need to do the data transformation, data processing. For the output, we just do min-max scalar transform, which is basically like normalizing it between the minimum and maximum. And this is actually a very important step for the neural network, because if your data varies by a large range, your neural network will not train. It will not be a well-trained neural network. And then on the third graph over here, I show the fitting between the transform data and the predicted data. By the predicted data, I mean the output that is generated using the neural network. And when all these moving pieces are ready, then I can do Bayesian inference and obtain this very specific kind of plots people in the field will know. These are called the corner plots, where we plot the posterior probability distribution of the individual parameters along the diagonal, and then in the inside, we plot the joint probability distribution. So what does it tell? So the posterior probability distribution tells us, okay, so in this particular range, so it gives you the lower bound and upper bound of your probability, and it tells you, okay, this is where I think, or this is where the walkers think my parameters lie. And then you get a peak at a certain point, and then it kind of tapers down to almost 0. And so for each of the parameters, I had 4 parameters in the one diode model: the shunt resistance, the series resistance, the ideality factor, and the saturation current density. So for each of those parameters, I get a certain posterior distribution. Alongside that, I also get this joint probability distribution. Joint probability distribution is where you plot the probabilities of 2 different parameters in a 2D plot, and then you can see where is the highest density of samples, and the highest density of samples lies where your ground truth should be. Also, from this kind of joint probability distribution, you can actually very easily see the correlation between certain things. So for example, over here, what I see that if I increase my J0 value, my NID also, and NID, the ideality factor at the same time, then I will not be seeing too much of deviation from my original curve, because these 2 parameters are correlated. So these are the kind of results that you can expect from your Bayesian inference. But well, there are lots of subtleties, and I will actually come to that, because that forms the most interesting part, I feel. So this was a very simple example that I showed, and everything seems to be working perfect, because also the parameters I found over here so I had a synthetic data for which I performed the parameter estimation for the one diode model, and it fits perfectly. I get almost the same values that I had originally used for my synthetic data. So it works. But does it always work? And that is what I'm going to discuss now. So there are a few things that I have learned over this year of how to make or what matters while you are trying to do Bayesian inference. One of the key things that I realized is that where you start your walkers in the Markov chain Monte Carlo. So for example, you have like, if your system is very well behaved, it will not probably matter too much. But if you have a very unbehaved system, by unbehaved system, I mean that like the slope or the derivative of the overall curvature of your system is not very smooth. So for example, delta function is not a well-behaved system. it changes suddenly, right? But like in our case, say variation of one parameter will not change my output very randomly. There is a slow and gradual improvement in the output as I vary the input parameters. So that is a well-behaved system. But just in case if your system isn't well-behaved or you don't know what it is better to find out a good starting point for your workers. And by good starting point, I mean that you need to find a point which has a high likelihood. And this I do by actually I use a genetic a covariant matrix genetic algorithm to find a good starting point for my workers. So I say in my code, I refer to it as the best starting point or the best point. So before I run MCMC, I actually find a point that fits my data. And then I let the worker start from there. So it already is at the highest likelihood point, and then it kind of crawls down and searches the whole space to find out till where my, or in what range my probabilities can vary, or what is my 90% credibility interval, which is like, where is the 90% chance of my parameter being present, right? So this is an example where these two graphs are from different starting points, and you can see that the posterior distribution actually varies quite badly. So over here, I found a high probability point and then started the walkers. And in this case, I didn't. I just started it randomly. And you see these multimodal distributions. So this was an unbehaved system. And why this happens is because suppose some of the walkers start in a local minima where there's a dip in the system, like, it's varying. And then if it is in the local minima, then there's a high chance that the walkers might get stuck there and it will not sample the entire space. And this kind of problems lead to multimodal distribution, or your MCMC not converging, or it's taking forever to converge. Okay, and actually also it can also, if you look at these two graphs, so this is the paper we were talking about where Tonio's group was trying to map the temperature with some of the output material parameters, and you see that from two different distribution, I get two different ranges of surface recombination velocities. And also the kind of the trend also changes. Like over here, you have a more of a curvature kind of thing on the left, whereas on the right, you have a more like straight or linear relationship. So it's very important that you do start your walkers from a high likelihood point. Another problem with Bayesian inference is that how, like, the training set or the size of your training data set. So your surrogate model is trying to assume the part or like work as the alias of your device simulator. But I mean, you can train it only so much well. Like there would always be a validation loss at the end of the training. And the thing is that the lower your validation losses, the better. For example, over here, I have the output from this two, like on identical data set, on the same data set with two different validation losses. And you can see that over here, my like my joint probability distributions are far more defined on the left-hand side than on the right-hand side because I had a lower validation loss. And so if you are having problem with convergence of your MCMC, then another thing one can do is actually trying to increase the data set so that your neural network is actually better trained or have a lower validation loss. Another thing, and this problem I found it most interesting, and this kind of forms the core part of my project, is that at least in perovskites, we have tons of unknown parameters. Like first I was using 10 unknown parameters, then I reduced it to 8, but there's still a lot. And what I saw is that, so I had two experimental data sets. One was illumination dependent current voltage characteristics. The other one was illumination dependent Fermi level splitting inside, which we got from voltage dependent photoluminescence data on the same device. And so first what I did, I just did a parameter estimation just using the 4 current voltage curves. And I got kind of quite beautiful fits if you see on the left, right? They almost, they absolutely reproduce the VOCs, also around the maximum power point, the fit is quite good. But then I used that same material parameters to try and fit the Fermi level splitting data, and it completely does not work. And so one thing I learned is that when you are doing parameter estimation on with large number of material parameters, it is always better to kind of double check that the parameters you are using or parameters you are getting from one data set, does it reproduce the data from another data set or another kind of factorization data of the same device. And then we actually then combine these two data sets. So I generated like another set of simulation data to now train my neural network not only on the JV data, but also on the Fermi level splitting data. And so my neural network in the end could actually predict the JV data and the Fermi level splitting data at the same time. And then I did another batch of parameter estimation using that data. What I would say that, okay, the JV curves definitely, the fitting to the JV curves definitely deteriorated. But now, if I look at my internal voltage versus external voltage data, it has a much better fit. At least it is closer, right? So yeah, so this is another thing when we are dealing with large number of unknown parameters, double check with different characterization data. If it doesn't match, then maybe do Bayesian inference by combining different data sets, and that could help. Another problem that comes here is that we are still using a model data, right? A device simulator. And how do we actually know that my model actually represents my system? For example, in Perovskite, we have ions, the mobile ions, but in case of my device simulator that I used, it did not have ions. And that's the thing that I also need to do next. And so I already know that there is some discrepancy between my actual device and my simulator. But it might not be always obvious that there is some discrepancy. So how do you know that? So we can find that out by eliminating the other problems. So a method of elimination. So first, train your surrogate model as much as you can so that the validation loss is really low. This is important because the Bayesian inference system runs on your surrogate model. If your surrogate model has a high loss, then the Bayesian inference cannot accurately calculate the likelihood function. There is a higher error percentage in the likelihood function. And if the likelihood function is not well calculated, then it will also skew your parameter distribution or even your Bayesian inference might not converge in the end. So yeah, another thing is that understand what parameters are going into a device simulator and which ones matter. So maybe do a feature importance ranking or a SHAP analysis, which can tell you that which of the parameters you are varying matters the most, or which parameters has the highest impact on your data. Then try different experimental data sets and see that, like suppose you are getting some parameters from one data set and one kind of experiment and some very different parameters from other experimental data set, then probably it's a problem with the model. Then it does not involve all the physics that are necessary to describe your data. Also, another thing is that figure out if there are some systematic discrepancies that you can see in your data. Like, for example, I'll go back to this figure over here. So what I see here is that my predictions they are sort of underestimating my Fermi level splitting for lower illumination intensities and overestimating it for the higher illumination intensities. And I see a very similar sort of discrepancy also in my JV data, because here the discrepancies for the higher illumination intensities are higher, whereas for the lower illumination intensities are lower. And one thing could be that when we have ions, or maybe the ion density in the devices are actually illumination dependent. So there are more ions when we have higher intensity and lower ions when we have low intensity. And so the model kind of is more close to reality when there is low illumination intensity than when there is more ions in general. So there is no easy answer to how to know your model is good enough or not, but you have to check out a number of things to eliminate And I mean, over time, you would understand by looking at the graphs that what might be the problem. So yeah, this is what I did. It's almost time. Yeah, so one thing we can improve in our code is that right now, the code always runs with uniform prior distribution that I have no belief in my, I have uniform belief in my initial set of data. But one thing we could do is to actually use the posterior probability distribution from one of the data sets and use it as the prior to the next experiment. And then I also want to try different device models and see if there is an improvement in results, like I was talking to Vasu about it. And finally, I'm looking forward to actually use this system for other kinds of data from other devices, because then it would be like a run for not only other kind of physics, but I mean, probably those systems would be much more difficult or easy. I don't know, but it would be interesting to see. And definitely, I personally, and I think always looking to collaborate with people on this thing. Also for code development, or if you have an interesting system, then we can look at it together. Thank you. And before actually I forget, yeah. And also I want to thank, I kind of forgot to put the acknowledgement slide. Yeah, so this work was funded by DAAD last year. For 1 year, they funded me as an exchange student. And Tonio hosted me at SMART and MIT, and also supervised by my supervisors at Forschungszentrum Jülich and RWTH Aachen University. So a huge thanks to all the people involved who made this happen. Thank you.